Z-score or standard Z-score measures how many standard deviations a data point X is away from the mean mu. And the formula is Z is equal to X minus mu upon sigma, right? Where sigma is the standard deviation. So it basically measures how many standard deviations a data point X is away from the mean. If you only have a sample, use the sample mean and a sample standard deviation, right? Z is equal to X minus X bar upon S. So interpretation is, if Z is 0, the value equals the mean. That is 1 standard deviation above the mean. That is equal to minus 2 standard deviations below the mean, right? Why this matters? Z-score standardizes different variables to common scale, enabling comparisons and probability lookups using the standard normal distributions. Next, what is the time complexity of self-attention? It is O of n square. So in standard self-attention, each token computes attention scores against every other token. So we compute Q times K to the power, compute Q times K transpose, where Q and K are n cross D. Multiplying n cross D by D cross n gives O of n square times D, and linear head dimension is D, which is constant. So we have O of n square, right? Hence we have quadratic complexity in n. Calculate 20% trimmed mean for values. So step by step we'll be looking at that. A 20% trimmed mean removes the lowest 20% and the highest 20% of observations and then averages the rest. So 20% trimmed mean. So for n is equal to 10, that is the number of elements in this list that has been given to us. 20% of 10 would be 2. So remove the two smallest and the two largest values. So once we sort the data, we remove the two smallest, 3 and 4, and the two largest, 15 and 16. And the remaining data is 5, 6, 7, 9, and 12, 11 and 12, right? Then we sum these up. Once we have summed this, we get the count, that is 10 minus removing 2 from the beginning and 2 from the end. We get 6 elements left. So sum upon count, that is 50 by 6, is 8.33, and that is our answer. Now find the interquartile range. If Q1 is 46 and Q3 is 58, interquartile range is Q3 minus Q1. So IQR becomes 58 minus 46. IQR measures the middle 50% spread, and it is robust to outliers. Now, is the test performed when the data is not normally distributed? The answer is Kruskal-Wallis test. So parametric tests like Z-test, T-test, and ANOVA, all the other options, assume normality or large sample sizes via central limit theorem, right? So they are using normal distribution. But Kruskal-Wallis test is a non-parametric alternative to one-way ANOVA when assumptions, that is normality and homoscedasticity, are violated. It tests if median ranks differ across groups. Examples: for two groups non-normal, use Mann-Whitney-U, Wilcoxon rank sum. For greater than two groups non-normal, use Kruskal-Wallis. Now, which method is used to control the rate of reporting false positives? That is multiple hypothesis testing. In the context of multiple tests, we need procedures to control error rates. Two widely used concepts are family-wise error rate, probability of at least one false positive, and false discovery rate, FDR. So the practice of multiple hypothesis testing correction is used to control false positives, right? Now Ria found the correlation as minus 0.69 between foot length and height. What does this signify? It means height and foot length are strongly inversely correlated, because Pearson correlation is equal to minus 0.69 is moderately strong negative correlation. As one increases, the other tends to decrease. Negative sign also indicates inverse relationship. Magnitude around 0.7 indicates the strength of it being negatively correlated. And correlation also does not imply causation. That is another important point, which we have discussed in our previous videos. So relationship between mean, median, mode for positive skewness, right skew, mean greater than median greater than mode. So for right skew distributions, long tail to the right. Let me show you visually. So right skewed distribution looks something like this. Long tail is to the right. So right skew means this, right? Or let me just draw the x and y axis in this format. Right skew is this. Long tail towards the right. The mean is pulled to the right, right? The mean is actually, if let us say the mean was here, the mean is pulled to the right most, that is the largest, right? Then mode is at the peak left of median. Mode is at the peak left of median, and the median is between mode and mean, right? Tail will basically tail to the right drags the mean higher. What does kurtosis explain in terms of distribution? It explains the flatness of distribution, the peak or tail behavior. So kurtosis quantifies the tailedness and peakedness of a distribution relative to a normal distribution. High kurtosis means heavy tails, sharp peak, and low kurtosis means light tails, flat top. High kurtosis means, let me explain this again. High kurtosis would mean, just a second, heavy tails and sharp peak, right? Like a sharp peak and heavy tails, so something like this. And low kurtosis would mean light tails and a flat top, something like this. This is low kurtosis and this is high kurtosis. So flatness, peaked versus flat, is the intended meaning. Also, people say kurtosis measures tail heaviness rather than flatness only, right? Moving on, which is not true about dropout in transformer. Dropout is applied to output of each sublayer, true. It is done before being added to sublayer and normalized, true. It is applied to sums of embeddings and positional encodings in both encoder and decoder stacks, true. It is applied dropout only to the sums of embeddings, that is false. So dropout is applied to sublayer outputs, attention and feed forward true. Pattern was this: dropout occurs before addition and then normalization, and also dropout was also applied to the sums of token embeddings and positional encodings that model input to. These is false because dropout is not applied only to sums of embeddings; it is applied at multiple points, right? To attention weights, sublayer outputs, and embeddings. Moving on, we have query key value matrices. So in transformer self-attention, QKV matrices are linear projections of the input tokens that convert each token into three different views used to compute attention. So let us say we have an input, a sequence of token embeddings X with shape n, d model, dimension of model, where n is sequence length and d model is the model dimension. Linear projections, Q is equal to X times WQ, K is equal to X WK, and V is X WV, right? So WK, Q, WK, and WV are basically, that is, these entities are basically the learned weight matrices, and we have shape d model comma dk for Q and K, and d model d comma dv, that is m cross n matrix. So d model cross dk for Q and K, and d model cross dv for V. Now what each represents: so query q is the question representation for each position. What am I searching for in the sequence? And when computing attention for position I, we use that row of q as the query. Then we have key k, the index representation of each position. It describes what content each position offers, right? So it dot product between q and k, qi and kj measures compatibility between the query at I and key at j. And value v is the actual content response at each position. When keys match queries, we use the corresponding values to produce attention outputs. And this is the formula: attention QKV is softmax of Q times K transpose upon root DK times V dot product V. Right. So first we compute the square matrix. S is equal to Q dot product with K transpose upon square root of DK dimension K. Right. And then we apply softmax across each row, which gives attention weights, how much position I attends to each position J. Multiply or dot product with V to obtain a weighted sum of value vectors for each token. Why scale by root dk? To avoid very large dot products when dk is large, which push softmax into regions with tiny gradients. Dividing by it keeps the variance stable. Right, moving on, BERT architecture. So BERT stands for bidirectional encoder representations from transformers. Is a transformer encoder only model trained with self-supervised objectives. This is a schematic diagram you can see. Right, so some key components I'll discuss. We have input embeddings here, token embedding plus segment embedding plus positional embedding. Right, token embedding plus segment embedding plus positional encoding summed. Then we have the encoder stack L with L identical as BERT base. L is equal to 12, D model is 768, heads are 12, and BERT large is L is 24, D model is 1024, and heads is 60. Then we have pre-training tasks: original word, masked language model, and next sentence prediction. MLM and NSP are two important characteristics of BERT model, which are the pre-training tasks for original word. So MLM, masked language model, masks 15% of tokens and predict them, enabling bidirectional context. And next sentence prediction, binary task to predict whether sentence B follows sentence A, used for tasks involving sentence pairs. How to use BERT: token classification, find tune BERT with classification head per token, then sequence classification, and question answering. Right. Moving on, we have softmax function. It basically converts a vector of real numbers, logits, into a probability distribution over classes. Converts a vector of real numbers into a probability distribution over classes, and this is the formula. Softmax is basically softmax of any, let us say, z of I is actually e to the power z of I and summation e to the power z of j, where j goes from 1 to k, right? I goes from 1 to k as well. So properties outputs values in 0 to 1 range and sum to 1, valid probability distribution, smooth and differentiable. It is suitable for gradient descent. And also softmax is often used with cross entropy loss for classification and can be used for temperature scaling as well. Softmax z upon t for t greater than 0. Larger t makes the distribution softer, more uniform, and smaller t makes it sharper. And then we have the Jacobian form as well for derivative. We can go through that. Finally, we have multi-head attention. What is it and why? So multi-head attention runs several attention mechanisms, heads in parallel, each with its own linear projections for Q, K, V, then concatenates their outputs and linearly projects the result. Formally for H heads, for ith head we have this, then concatenate, right, for each head. Why multiple heads? Each head can attend to different types of relations, syntax versus semantics, short versus long range. Smaller head dimensionality, k is equal to d model upon h, makes attention manageable in computation. Still, multiple heads yield richer representation than a single large head. Finally, we have positional encoding. So self-attention is permutation invariant. It has no inherent notion of token order. So to encode the sequence order and get positional information, we use positional encoding into token embeddings. So we have fixed sinusoidal positional encoding for position pause and dimension I. This is the formula that I've already discussed in the last video. So this gives each position a unique vector, enabling model to learn relative positions because sinusoids allow linear combinations representing shifts. We're using sine for the even index 2i and cos for the odd index. Learned position embeddings, a table of max length times dimension model that is trained along with token embeddings used in BERT and many models. I've applied some token embedding and position embedding, right? And finally, we have a feature engineering. It is the process of transforming raw data into features that better represent the underlying problem to improve model performance. Transforming raw data into features better representing the underlying problem to improve the model performance. It's a representation problem. Choose what the model sees. Uses domain knowledge plus statistical techniques plus creativity, also called data wrangling or data munging. So common FE tasks: feature engineering, imputation of missing values, mean, median, model based, categorical encoding, one hot, ordinal, target encoding, embeddings, then scaling and normalization using min-max scaling or Z-score, robust scaling, pinning, discretization, then feature creation, time series features, text features, backwards, TF-IDF, word-to-vec, and also feature selection, remove irrelevant or multi-collinear features using PCA, lasso, right, or tree-based importances, right? So why it's important? Good features can drastically improve performance and reduce the model complexity, and feature engineering is often the most time-consuming and impactful part of ML. Then we have parametric versus non-parametric tests. So parametric tests assume data following a specific distribution commonly normal. Examples: t-test, pair t-test, ANOVA, z-test, linear regression. It has more statistical power when assumptions hold. Interpretable parameter estimates, and we have assumptions that normality is uh, the distribution is normal, independent, equal variances, that is homoscedasticity is there in data. For non-parametric tests, they make no strong distribution assumptions, work with ranks or orderings. For example, Mann-Whitney U for two groups, Wilcoxon sign rank for paired, Driscoll-Wallace for multiple groups, and Spearman correlation. It is robust to non-normal data, outliers, and small samples, less sensitive to distribution. Disadvantages: sometimes shows a lower statistical power when parametric assumptions hold. Interpretability in terms of medians or ranks rather than means. Right? Decision flow is check assumptions. Normality tests like Shapiro-Wilk visualize via QQ plot. If the assumptions hold or larger samples per central limit theorem, use the parametric tests. Else, if the assumptions don't hold, that is, if the distribution is not normal, or if there is no homoscedasticity or independence, choose non-parametric. So for paired data with non-normality, use Wilcoxon sign rank instead of paired t-test. For greater than two groups non-normal, use Driscoll-Wallace if significant. Follow up with post-hoc pairwise tests with multiple comparison adjustment. Now, z-test versus t-test distinction. Z-test is used when population standard deviation sigma is known, which is rare, or sample is large and greater than 30, and use the formula z is equal to x bar minus mu upon sigma by root n. T-test used when population sigma is unknown. Use sample standard deviation s and t distribution with n minus 1. T is equal to x bar minus mu upon s upon root n. Right? And correlation versus causation. Correlation detects association. Pearson measures the linear association. To infer causation, we need the randomized control experiments as a gold standard, or causal models like directed acyclic graphs, instrumental variables, differences in differences, or natural experiments, and strong domain knowledge. Beware of confounders, selection bias, collider bias, right? Now, kurtosis or mathematical details. Excess kurtosis is kurtosis minus 3. Normal distribution has kurtosis 3, so excess is 0. Positive excess kurtosis has heavy tails and negative has light tails, right? And that's it.